we know her since the beginning of quantum law. And she's actually one of, a long, long time ago in Oxford, there were many witches, and she was one of them. So today we have a visit from the witch who will talk about quantum resource theory, and also a little bit about Dagmar Bruss. She was the head of department. Are you still the head of department? Oh, you just stepped down. But she was the head of department for some time at this university called Heinrich Heine. I don't know how to pronounce it.
Heine.
Yeah, it's a poet. Duesseldorf, in Duesseldorf. And she's been there for a long time. Before that, she was in various positions at Hanover, Oxford,
Turin.
Yeah, and other places. And I think she's also been on the advisory board for Munich, in the advisory board for Max Planck.
No.
No?
No.
Okay. If you're not, you're not. Then I thought you were in some scientific advisory board for something.
Yeah, for something, but not.
Some advisory board. So, without further ado, I think I'll let Dagmar does the talk, and let's give her a round of applause.
Thanks a lot, Greg, for the very kind introduction and for calling me an old visitor of CQT, which is actually true, and for giving away all the secrets about our witchcraft from Oxford. I thought that it should remain a secret, but I will actually tell you some of the secrets of our recent witchcraft, which doesn't involve the other witches, which is really bad. So don't tell people who are the other witches. And, well, it's actually my first. There were, yes, at least four. But no names. I'm the only one given away now. So actually, it's the first time that I do this kind of long-distance travel after the pandemic, and it's really great to be here again, to see a crowd of people and to talk to you in person, not just in front of a computer. So thanks a lot for having me. And let's see. To revive this. Well, today I want to focus on one recent work that we did in Düsseldorf. And the main credit goes to Lukas Tendig, who's a PhD student in my group, very clever, very energetic, full of ideas, and he's about to finish soon. Then there is Martin Kliesch, who was a junior professor also in Düsseldorf, but recently moved to Hamburg as a full professor. Hermann Kampermann, who is a very important member of my group. Actually, he's running the group now when I'm traveling to Singapore. So while I'm having fun, he has to do the work. And I'm very happy that he has been there since the beginning of when I started the group in Düsseldorf. Well, I hope that the talk will not be too technical. Let me try to be concise, but not over-technical. What I want to tell you about is a work that we did on resource theories for measurements, in particular for sets of measurements. And maybe to give a very brief summary, we introduced a measure that has not been used before, and it's a distance-based measure. And these distance-based measures, they have very nice properties. And then you can prove nice things with such a new measure. That's somehow in one sentence the summary of my talk. But let's go through it. For those of you who are not so familiar with resource theories, I will make a little reminder of resource theories for quantum states. But today I'm going to talk about resource theories for quantum measurements. And they look, in principle, quite similar to those for quantum states, but there are some differences which I will point out. And here I'm going to talk about several measurements, so about sets of measurements, and how to quantify the resource that is contained in such sets of measurements. And one result that we found was that if you have a given set of quantum measurements, then you can describe various resources. Like I will mention some of them: incompatibility, informativeness, coherence, You can think about steerability. And we showed that there is a certain hierarchy of these resources, which is in a certain way analogous to a hierarchy of resources contained in quantum states. And if there is time, I will also look at some further implications and observations. Maybe I will talk a little bit about recent work that we did on certain inequalities for sets of measurements when you add another measurement. So let's say you have already two measurements, like in BB84, you measure in Z and X direction, and then you add a third measurement. And what is the gain in incompatibility that you can achieve? And there are certain inequalities that are very similar in a way to monogamy inequalities for entanglement. So this is our latest observation, let's say, and let's see whether I get there or not. And if you want to read up the details and the technical stuff and the proofs, it's a paper that has been on arXiv already for quite some time. And actually yesterday we got the report, so it should be published in some time, I hope. So this is my reminder slide for resource theories for quantum states. And there is a beautiful review on this topic written by Eric Chittambar and Gilad Gur, Review of Modern Physics in 2019. So basically all resource theories for quantum states look more or less the same. So it's an elegant general description. And this picture illustrates what are the ingredients of such resource theories for quantum states. So here you see this blue egg-shaped set of states. These are the so-called free states, which do not contain the resource, but they are easy to produce and they don't cost much. So the first ingredients are the free states in this blue convex set. So typically resource theories have a convex set of free states, and they're called convex resource theories. And everything that is outside here, this red area, those are the states that carry the resource. The second ingredient are so-called free operations versus operations that can increase the resource. So what are free operations? Free operations are those ones that cannot increase the resource. So here in this picture, let's say we are inside the set of free states. We have one free state, sigma 1, another sigma 2. And with a so-called free operation, lambda is a completely positive trace-preserving map, anything that you can implement in the lab. So with such an operation, a free operation, you can never, acting on the free state, you can never go outside of the set of free states. You cannot produce the resource from nothing. If you want to go outside of the set of free states, you need some operation that creates the resource. And it's more difficult to implement in the lab. Well, the last ingredient that you need, well, if I put it in very simple terms, is a quantification of the resource. So for instance, here in the set of resourceful states, you have one state rho 1, another state called rho 2, and one possible quantification of the resource is a distance. So you could take the closest distance, the distance to the set of free states here. And I already called this D1, and the distance of the state rho 2 to the set of free states will be D2. And again, if I have a free operation lambda acting on rho 1, it can only decrease the distance, not increase it. So this is basically the main idea of resource theories for quantum states, and all of you know a very famous example for such a convex quantum resource theory where the set of free states is convex, namely entanglement. So there the free states are the separable states, the resourceful states are those ones which are not separable but entangled. The free operations are local operations and classical communication, which cannot turn a separable state into an entangled one. And if you want to create entanglement, you need other operations like a control NOT gate or whatever. Quantification of entanglement goes via distance measures or robustness measures. I will talk more about these measures, or concurrence or whatnot. So that's in a nutshell a resource theory for quantum states. And let me point out that for quantum states, you have a certain hierarchy of the resources. So if you are given the particular quantum state rho, then in some recent work, with Alex Strelzow, Hermann Kampermann, Sabine Wölk, and Manuel Gessner, we showed that the purity of a given state is the resource that bounds all the other resources. So the purity, so the coherence can never be larger than the purity, the discord can never be larger than the coherence, and the entanglement can never be larger than the discord. So there is a certain hierarchy, and maybe let me not go into the technical details. So if you allow for unitary global operations, then purity is the resource that bounds everything else. And here in the picture, maybe let's look at the small picture only, because that's for qubits, and qubits are always easier to handle. So in the small picture, you see the Bloch sphere, the Bloch ball. In the middle, there is the identity normalized, so the identity times 1/2. And on top, you have the pure state ket1. On the bottom, you have the pure state ket0. And the line connecting these two states are those density matrices which are incoherent because they are diagonal in the computational basis. So the coherence of a given state rho that lies somewhere inside the Bloch ball is the distance to this vertical line. That's the coherence. And the purity, instead, is the distance of rho to the equally distributed state to the identity. And then it's pretty clear that if you want to maximize the coherence of a given state, and you're allowed to do unitary rotations, you just rotate the state into the xy plane. And then you get this red line, which is the maximal coherence that you can get from a state rho by applying unitaries. And the big picture that just says that this kind of almost intuitive fact also holds for any dimension. So for qubits, everything is easy because you have this Bloch sphere, which is connected, but for higher dimensions, you don't have such a simple picture. You have a higher dimensional Bloch object, but it has holes and things. So this general notion of this hierarchy holds also in higher dimensions. That's all I want to point out here. And in fact, what we aimed at was trying to find some analogy for measurements instead of states. So this hierarchy holds for resources of states. Good. So let's now turn to measurements, which are really the topic of this talk. And let's remember what we know about measurements. What is a POVM, a positive operator valued measurement, the most general measurement that you can do. Mathematically speaking, it's very easy. It's a set, M, that consists of so-called POVM elements, M with index A, which are positive semi-definite, and they add up to the identity in a d-dimensional Hilbert space. So small d is always the dimension that we are talking about. And A is the index for the outcome if you make this measurement, and it can go from 1 to d for sure, but also it can take more outcomes, so you don't need to be restricted to d POVM elements. What is the probability to get the outcome small a? Well, it's the trace of the operator M with index A times rho. That's a POVM that all of you know. And let's remember to set our mind in this direction. One example, very famous example for a non-trivial POVM. So for Neumann measurements, which are projective orthogonal measurements, I would call trivial POVM. But if you have the task of unambiguous state discrimination, then the best thing that you can do is a measurement that is not orthogonal projective von Neumann measurement. So what you can do then is, or what is the best measurement here in this situation is as follows. I think also it's known to everybody, I just repeat. So you're given two states, ket vector phi and ket vector psi, which are non-orthogonal. So this is the Bloch sphere, or an intersection through the Bloch sphere. And the task is to distinguish between these two states without making a mistake. So you're allowed to say, for sure I found state phi, or for sure I found state psi, and you're allowed a third outcome which says, I don't know, I cannot commit. And this corresponds to 3 POVM elements. So the first POVM element is this red one, M with index phi, that is orthogonal to the state psi. So on the Bloch sphere, lines that have 180 degrees mean that things are orthogonal. So if you get outcome phi, you know for sure that you have not found psi, but phi. Equivalently for m psi, and then in order to make the POVM elements add up to the identity, you need a third POVM element, m question mark, and if you get the question mark outcome, you say, I don't know. That's the task of unambiguous state discrimination. So here the POVM is a set of 3 POVM elements. Good, everything known so far. Now let's go one step further. Let's look at sets of measurements, so sets of sets. Sometimes such a set of measurements is also called a measurement assemblage because it's a collection of several measurements. So we need another index. The index for the measurement setting will be x, and this index can run from 1 to m, small m, so small m is the number of measurement settings. And, well, in principle, each of these measurement settings can be chosen with a certain a priori probability p of x. Where do you need such a situation? Well, in several places. If you want to prove, for instance, Bell non-locality, you have to make more than one measurement. If you want to prove steering, yes, you also need more than one measurement. In QKD, you need to do measurements in different base, you need to do more than one measurement. So it occurs very often that you need several measurement settings, and we want to understand what is the resource contained in these sets of measurements. So such a measurement assemblage, now I use the same letter, so don't be confused. This calligraphic M in general denotes a set of measurements with 2 indices, so X is the index for the measurement setting, and A is the index for the outcome of a particular measurement. So each of these operators, MA given X, is positive semi-definite, and for each setting X, the sum over all A, M of A given X, is the identity. Well, here I said that these measurements can be chosen with a certain probability. So in principle, you also have to add another quantity, this vector P, and then you get a tuple that consists of your set of measurements or your measurement assemblage with certain probabilities, or you call it a weighted measurement assemblage. And the probability to get outcome A for a given measurement setting, P of A and X, you get it by the a priori probability P of X times trace of MA given X times rho. But for most of the talk, I will drop this kind of a priori probability because it just makes life more complicated. Everything that I'm telling you can be done also for weights, different weights put on the measurements. So let's again look at an example. So here, for instance, if I want to show a violation of the Clauser-Horn-Shimoni-Holt inequality, both Alice and Bob need to employ 2 sets of measurements. So, for instance, Alice here in red, the first measurement that she can do is in the Z direction, so she has one POVM element which is projector onto 0, the other one projector onto 1. The second measurement is, for instance, in the X direction, so one projector onto eigenstate X plus, the other one on eigenstate X minus, and then Bob also does 2 measurements in a rotated way. So these are the sets of measurements. And the questions that we asked ourselves were the following. We wanted to quantify the resources for these sets of measurements, and we wanted to understand whether there are relations between different resources for a given set of measurements. And of course, we're not the first ones to look at resource theories of measurements. There have been many people working on this, and I just list here 3 papers, and by no means this is complete. I don't know, maybe some of you are also working in this direction, so don't be offended if your paper is not there. So, for instance, Skripczyk and Linden, Osmaniec and Biswas and Gaff et al. Have worked on resource theories for quantum measurements, and now you see basically the same picture that I showed you before. But now the sets consist of measurements or measurement assemblages. So again, you have this blue egg-shaped object, which denotes the free measurements or the free measurement assemblages. Then you have free operations, And I will talk in a moment what are these free operations between sets of measurements. And these free operations can only convert one measurement assemblage to another one that is free. So you can only stay inside the free measurements. And on the other side, outside of the set of free measurements, you have the resourceful measurements. And if you want to, increase your resource, you have to use operations that are not free. The main question that we were addressing was then the quantification of the resource. So what are the ingredients for resource theories of sets of measurements? Here in a little bit more detailed or concise way. The first ingredient are the free measurements, and let's call them calligraphic F. And they consist of a set of FA given X. So for instance, if you have measurements that are a sum of projectors onto orthogonal basis states that I denote as I, with certain coefficients, then you would have diagonal measurements, and they would be the free states in the resource theory of coherence. So by fixing your set of free measurements, you fix the corresponding resource theory. What are free operations in this context? I said for the state, you have completely positive and trace preserving operations to convert one state into another. For measurements, you have two possibilities. The first one is linked to these CPTP maps that I talked about before. So remember that if you have such a CPTP map lambda acting on rho, I didn't say this before, but I think everybody knows that it can be written via Krauss operators, K mu acting from the left and K mu dagger acting from the right on rho, summing over mu. So every CPTP map can be written in terms of these cross operators, and you can connect to that, or this corresponds to the adjoint map, lambda dagger, acting on the measurements operators in the following sense. Let's look at what are the probabilities for getting the outcome A given X. Remember that this is the trace of the P of M element, MA given X, times the map acting on rho. And now you write it in terms of cross operators, and under the trace, you can permute the operators that are written there, so you can pull the K dagger to the front, which means that you can interpret now the action of K mu dagger from the left and K mu from the right onto the measurement operators as the adjoint map. So you can describe these general maps on measurement operators. This is one way, and then of course if this map does not increase the resource, then it's a free operation. A second possibility for operations on such measurements is the so-called mixture and classical post-processing map, where you get a new map, M prime, which is some function psi of M, by just combining the old elements in a new way. So you start from the old POVM elements, MA given X, you put some probabilities on top of them, you sum over A, and you have probability of P of X given Y, again summing over X, and this gives you a new POVM element that you can create from the old ones just by mixing the old ones and putting some probabilities. So this is also a possible map that you can use or apply to measurement operators. And the last ingredient is the quantification of the resource. So you want to find a so-called monotone that measures the amount of resource that is in the measurement, which has certain properties which are very analogous to, let's say, entanglement theory. So maybe it's a bit boring, but I have to repeat these things. So the resource monotone R of calligraphic M is 0 if and only if M is an element of the set of free measurements. So this should not be calligraphic F, but the set of free measurements. Second requirement for such a good monotone is that if you act with this lambda dagger free on a measurement, then the resource cannot increase. Third ingredient or requirement if you act with a free mixing and post-processing map psi on your measurement m, then again your resource should not increase. You can only decrease by acting with such a free map. And finally, convexity. So if you have a convex combination of two measurements, calligraphic m and n, then this is smaller or equal than the mixture of the resource of m plus the corresponding part resource of n. So basically, these are the same ingredients. There is a question?
Yes. So do you have any systematic way in your mind to define this lambda Dagmar free measurement in relation to the state theory?
It depends on the situation that you're looking at. It's not clear. It's not clear how to get the free operation. It depends, of course, on the set of free measurements that you define, and it's not a simple question. So
are you trying to define this lambda Dagmar free independently from the...
It may be. So quite often one looks back at the resource theory of states. For instance, if you look at the resource theory of coherence, there are many different ways to define free operations. You can have this maximally incoherent, this myo, thio, io, whatever there is. Probably there are experts here who know much better and have worked on this. So again, also for measurements, I think there will be different possibilities to define such free operations depending on the resource theory that you're looking at. But I think it has not been studied much. At least I'm not aware of that, but it's an interesting question, definitely. So, yeah, do feel free to interrupt any time. So, before I go on to say which measure we like to define as a resource monotone, which distance we liked, let me try to put some order into different types of sets of measurements. So there are different types of measurement resources. So there are resources that already exist for one individual measurement. So let's start with these because they are the most simple ones, resources of an individual measurement. And the most simple one is the so-called informativeness. What does it mean? Well, informativeness quantifies somehow how much you learn by doing a measurement. When do you learn nothing? Well, if you do a very stupid measurement. If you do a measurement that is proportional to the identity, you learn nothing because your outcome will not tell you anything about the state. So the free measurements in a resource theory of informativeness, all the free measurements F with index A are proportional to the identity, where the prefactors QA sum up to 1. That's the most simple resource theory of an individual measurement. The next one is so-called resource theory of coherence of a measurement. Again, you can have it for one individual measurement. And the free measurements there are given by FA, which I already had this example on the last slide. So you have a sum of projectors onto orthogonal basis states that are called ket vector I, with certain probabilities, alpha I given A, which are positive or equal to 0. And whenever you have such a diagonal measurement, it's a so-called incoherent measurement. So in the resource theory of coherence, the free measurements are incoherent, diagonal in a given basis from your side. Good. But we are also very interested in a certain property which is called incompatibility of measurements. And there you need more than one measurement. So a non-trivial resource of a set of measurements is the so-called incompatibility, which has been studied widely and is really one of the fundaments of measurement theory. And let's adopt a definition of incompatibility that is explained in a review article by Ottfried Güne and co-workers in the following way. When do we call a set of measurements free? A free measurement assemblage, f of a given x, can be simulated by one single so-called parent measurement, POVM, and deterministic classical post-processing. So if you can define one measurement that is characterized by the POVM elements G of G lambda, so lambda is an index, and G is the parent POVM, and you can multiply it with deterministic coefficients. So V denotes the vertices of a polytope, so it can be 1 or 0. But this doesn't matter, actually, whether it's deterministic or probabilistic. You can also do probabilistic post-processing and put the factor inside G of lambda, so don't worry about this fact. So you can get all elements in this assemblage from a parent POVM. So by making some higher dimensional measurement, classical post-processing, if you can do that, then it's a so-called free measurement assemblage. Good, so maybe what you have in mind from the quantum mechanics lecture is, well, if you have commuting observables, then they are jointly measurable. Yes, this is definitely true. So if you have commuting observables, they are jointly measurable, and for sure you will find such a parent POVM. So this direction is definitely true. But the other direction is not true. So if you have a free measurement assemblage or jointly measurable measurements, the operators do not necessarily commute. And there are counterexamples, and I will show you which are known in the literature. It's not us who invented them, but it's known, and I will show you one of these examples a little bit later on. So that's the definition of incompatibility. And again, going to the next step, there are situations when you need the resource in a set of measurements combined with the resource of a state. So it's not enough to talk about the measurements, like for incompatibility, but in addition, you also need to talk about states. And the famous example here is so-called steering, where you define measurements. So you have a composite quantum system, rho, quantum state, rho, and you make measurements only on one side of this bipartite quantum state rho. So let's say Alice measures here with the POVM elements, M of A given X. And if only she measures, then at the end, if you trace out her system, then Bob will be left with a density matrix. And this will be a state assemblage, so several states with the indices A given X. And if Bob's states can be simulated as coming from so-called local hidden state models, or you have some density matrix sigma lambda, again with some deterministic post-processing, then this is a so-called unsteerable state assemblage or free state assemblage. And the last point is so-called non-locality, where you again need a state, rho, a bipartite state of a composite quantum system, and you measure both on Alice's side and on Bob's side. So Bob has measurement operators n of b given x, and in the end you will get a probability distribution q of ab given xy. And if this probability distribution can be simulated from the product of two such deterministic probability distributions in the sense that I explained above, times some probability of a local hidden variable lambda, then you have a local probability distribution or a free probability distribution. So somehow these different types of resources are also in character quite different, because once you need at least one measurement, then you need more than one measurement, and finally you also need the states. But I will show that there will be a certain hierarchy that connects these different types of resources. So our task or our question was, can we develop a kind of unified framework for these different types of resource theories of measurements? And for that we needed a quantifier, and of course we are not the first ones who introduced a quantifier for quantum measurements. And a typical quantifier for resource theories of quantum measurements is the so-called robustness measure. And here is a typical picture that I stole from the paper of Osmaniec and Bruss. So it's not my picture, and it looks a little bit different from the picture that I showed before, but in essence it's the same. So here you have this convex set of free measurements, again in blue. Then you have a given measurement that lies here outside, given by M. And the robustness is defined as follows. You ask yourself, how much of another measurement N can you add to this measurement M such that you move from the resourceful part into the useless or free part. So what is the minimum of this parameter S, which has to be positive, such that there exists another measurement such that the sum of m plus s small n times n is inside the set of free measurements. So in a way, how robust is this measurement against adding some other measurement? That's why it's called robustness. And of course, many people use this robustness measure. Actually, recently in a completely different paper that we wrote also in Duesseldorf, we asked ourselves the question, when is it continuous? So this is a completely different side issue, but we thought that it was an interesting issue because in the literature it's not so clear when is such a measure continuous. Maybe your set of free states or measurements is not convex, but only star convex. So we looked into this question, and we came to like a little bit more these robustness measures because at the beginning we didn't like them. Why didn't we like them? Because they may be not well behaved. So they don't have nice properties. They don't have properties of distances. And for instance, for purity, the robustness will be infinity. Because for the resource theory of purity, you just have one point, which is free, and to move inside, you need infinitely much of a different resource. So this is my motivation slide, why we wanted something different. And we wanted to look at distance-based resource quantification for measurements, because distances are nice. So we wanted to introduce a resource monotone, R of m, that is the minimum distance of our given measurement assemblage, m, with respect to all free measurement assemblages. So why did we want to choose a distance? Well, because they have so nice properties. They are positive if m is not equal to f, they are symmetric, and they fulfill a certain triangle inequality, which makes your life easy when you want to prove certain things. But how do you define a distance from a set of measurements to a set of other free measurement assemblages? And the way that we suggested to do is, it's not unique. I think there are other ways to define distances in this context. So we suggested the following. To a P of the m, we associate a so-called measure and prepare channel in the following way. So for your given measurement m with setting index x, you take the probability to find outcome A. So you take the trace m of A given x times rho, and you multiply this with a kind of flag. So an orthogonal state A, and you have a collection of orthogonal states, and this defines you a channel. That's the measure and prepare channel. So you measure and you prepare your flag that tells you which outcome you got. And once you have defined this channel, you can use the so-called diamond distance between channels, which was introduced a long time ago. It's, again, not our merit. We just used it because it has nice properties. And this diamond distance between channels was introduced, I think, like 20 years ago, maybe, in the context of channel discrimination. So how is it defined? The diamond distance between two channels, lambda 1 and lambda 2, is defined as follows. You take the difference between the two channels, and you act, again, on a bipartite system only on one side. So let's say Alice applies the difference of these two channels, Bob does nothing, and then you maximize over all possible states in the state space, in the composite state space of your dimension that you chose. And the norm that you use is the trace norm. So defined as usually the trace of square root of x dagger x. And this is a good definition because it can be linked to the success probability in discriminating these two channels, and it also tells you something about entanglement-assisted channels, etc. So we just took it from the literature and suggest to use it in this context. Again, the paper that I cited before. Good, and now we are done because we can write down the definition of distance-based resource monotones from sets of measurements. And let's start with the most simple case, the informativeness IF diamond of a weighted measurement assemblage MP. So we take the minimum over all free assemblages, so from the set of uninformative measurements, so UI means uninformative, and then you take the distance, the diamond distance between each measurement, mx, in the set, and fx, and you put the weights p of x if you introduced weights before. So it's kind of an averaged distance for each individual measurement. And you can do the same for coherence. Now you see that the rest is a little bit boring on the slide because it's again the same. So for the coherence, the diamond norm, or the robustness, not the robustness, the distance measure of the resource theory of coherence for a given weighted measurement assemblage is as follows. You take the minimum over all free measurements in the set of incoherent measurements. IC means incoherent. And again, you take the weighted average distance. Now comes incompatibility, I for incompatibility. Now you take free measurements in the set of jointly measurable assemblages, JM. And again, you take here the difference. It's not an average, but you have to look at the property of the whole set of measurements, just to point this out here. You can define steerability. Here it's a little bit different because here we made already a measurement. So I don't put the diamond here because we're not talking about channels anymore. But we talk about the difference of the state assemblage that Bob gets after L is measured on the other side. And you minimize the trace distance of the sigma with respect to all local hidden states, tau. And finally, for non-locality, both parties measure and you don't get a state, but you get a probability distribution. So you just take the distance between this probability distribution Q and any probability distribution T from the set of local hidden variable probability distributions. So the trick is somehow that you use all the time a trace distance or corresponding distance between probability distributions, and that you manage to connect it to the channels that describe your measurement. And once you did that, then you get almost automatically a part of a hierarchy for these different measurement resources. Because if you look at the free sets for these different resource theories, then you have the set of uninformative measurements, and remember those were the ones that are proportional to the identity. And definitely these ones are contained in the set of incoherent measurements, because the incoherent measurements were diagonal, if you remember. So the identity is definitely diagonal, so it's contained in the incoherent set. And finally, if you have only incoherent measurements, they are always diagonal, so for sure they always commute, and that means that they are jointly measurable. So again, the set IC for incoherent is contained in the set jointly measurable. And that means if you have a distance-based measure, and here outside you have your measurement assemblage that you want to quantify the different resources, then automatically you see that informativeness is an upper bound to coherence, and coherence is an upper bound to incompatibility, simply because the distances are ordered like that. So in fact, what you can do is you can extend this hierarchy a little bit further. So here it's just a formal kind of theorem where we say that we have different measurements, and basically this text says everything that I explained to you before. You don't even need to read it. And what we found is this hierarchy that informativeness in this diamond distance monoton is always larger or equal than coherence, larger or equal than incompatibility. And this is also larger or equal to the steerability, and steerability limits from above the non-locality. So we can extend this hierarchy also to steering and non-locality. What is the idea of the proof? Well, the first two inequalities I explained already. The third inequality, connecting incompatibility with steering. The idea is that you use a state assemblage that comes from the closest jointly measurable measurements with respect to M, and then you have to show that this is an upper bound on steerability. And very similarly, you get also the fourth inequality by somehow looking at that assemblage that is the closest point in this distance picture, and then linking it to the next step in the hierarchy. So maybe I don't want to go into more technical details here, but you can read them if you want. So let's make an example. Examples are always good. You see some nice plots, some curves. And let's look at an example for this hierarchy, the so-called CGLMP measurements. Just in case, if you don't remember exactly what are the CGLMP measurements, they were introduced by Collins, Rizal, Massa, and Popescu a long time ago, 2002. So more than 20 years ago. I feel really old now, looking at these references. And what these authors did, they designed Bell inequalities for higher dimensional situations. So the measurements, so they looked at the maximally entangled state, phi plus, in d dimensions. So you just sum up the state ket vector II from I equal to 0 to d minus 1, the maximally entangled state in d dimensions. And then Alice makes certain measurements called M, A given X, and Bob does certain measurements called NB given Y in the dimension D. And here you see that M is a projective measurement, and you see the shape of these vectors, which doesn't really matter. So it's an explicit way to make measurements, but what we can do is we can now try to quantify the resource that is inside this pre-described set of measurements. And here you see our result. And well, now you should see 5 lines, no? You just see 3. Why do you just see 3? Because the informativeness and the coherence for this case can be analytically calculated, and they're given by 1 minus 1 over the dimension. So they are pretty large. Here you see on the x-axis the dimension from 2 to 9, and on the y-axis you see the amount of the resource going from 0.1 to 0.3. And for instance, for the dimension d equal to 2, you would have here 1 minus 1/2 is 1/2. So the two curves for the informativeness and the coherence are identical, and they lie somewhere up here. So they are not even on my slide anymore. So you just see the lower part of this hierarchy. And basically, well, luckily, it's true that the incompatibility in blue is always larger or equal than the steerability in orange. And this is always larger or equal than the non-locality. Otherwise, we would have had a problem because our proof would be wrong. So this is just an example for this hierarchy. But now you may ask, but how did you calculate this example? And so let me say a little bit about that. How can we actually try to make calculations for this distance-based resource monotone? Well, as very often, the answer is SDP, semi-definite program. And for the diamond distance, this has been done long ago, mainly by John Watrous, who has done a lot of work in this direction. So again, we are not claiming that we did this. We used previous results and, of course, had to reformulate some things, but the main ideas were already there. And then you can find numerical solutions, as we did in the plot that you just saw on the previous slide. But you can also find some analytic results, which is really nice. So if you have the primal problem of this SDP and you find a feasible solution, then you get an upper bound. And if you find a feasible solution of the dual problem, you get a lower bound. And of course, if the two coincide, you know that this is the exact expression. So we looked at mainly some results for incompatibility because somehow it's the most interesting resource for various reasons. And again, many people are interested in mutually unbiased bases. So we looked at results for MUB, mutually unbiased basis measurement assemblages, which are defined as follows. So you're given a measurement assemblage where each measurement operator is a projector onto a vector VA given X. And for X not equal to Y, then the overlap between these vectors is equal to 1 over square root d. So the usual definition of mutually unbiased bases. And here we could find analytical lower bounds and upper bounds for the incompatibility for this case, where d is the dimension again for our system and small m is the number of bases or number of measurements. And if you look closely at this lower bound and the upper bound, you can also see that for high dimensions, so for fixed number of measurements and large dimension, you find that the incompatibility will be 1 minus 1 over the number of measurements. So it's an analytical result. And for some time we were actually quite excited because we hoped that we could find out something about the existence of mutually unbiased bases in certain dimensions, certain numbers, like, I don't know, finding some results where the upper bound is lower than the lower bound and making some contradiction, but life is not so nice, so it didn't work. So the only thing I can say is that even if you don't know yet whether MUBs exist, if they would exist, we would immediately have these bounds. No? So for instance, the lowest non-trivial case is for dimension 6, and it's not known whether there are 4 mutually unbiased bases or not. And if somebody finds these, then we can immediately say that the incompatibility has certain upper and lower bounds. That's all we can say for the moment. Good. Let me see how I'm doing. Am I doing in time? I can say a little bit more maybe. Well, I will touch briefly. Well, maybe you ask yourself, we showed this hierarchy. Is it tight or not? Can it be tight? And that's, of course, the question we were also trying to understand. So we have 4 inequalities, and let's go through them quickly. I'm not going to show you the proofs, but just maybe say which ones can be tight and which ones not. So I already showed you an example where the informativeness can be equal to the coherence. If you remember the plot that I showed you, 2 lines were identical. In fact, for certain mutually unbiased basis sets, this inequality becomes an equality, so this can be tight. Let me go. Maybe I don't talk about the proof idea, but go one step further. The third inequality between incompatibility and steering, again, this can be tight. So again, we have an example for a certain state, the maximally entangled state, and certain MUB measurements with certain number of measurement directions. We could show that, in fact, for this situation, also this inequality can become an equality, so it's also tight. There are examples for tightness. We conjecture that this tightness holds for almost all MUBs, but we were not able to prove it yet. And so 2 inequalities are remaining, the second one and the last one. And we did some numerical studies and could not find any case where they are identical. So our conjecture would be that they are true inequalities, but again, we couldn't prove it. So we would need some further research in this direction. Well, that's all I wanted to say about this hierarchy. Maybe, I don't know, are there questions at the moment? Because if not, well, everybody looks a little bit tired. Maybe I just will say 1 or 2 words about what we have been doing since. And it's not published, but we were quite happy to get some interesting results. So let me just sketch the main idea, what we were doing after this work. We were asking ourselves, well, how can you quantify how much incompatibility you win when adding another measurement? Like I mentioned at the beginning, let's imagine you do QKD, BB84, you have 2 measurements, one in Z direction, one in X, and now you take, to go to the 6-state protocol, you take the 3rd direction. So how does the 3rd mutually unbiased basis? So how does your incompatibility change? What do you win? That was our main question. So you want to know what is delta I, where now I have to say what I mean by an assemblage. So this M with index 1, 2, 3 is now an ordered list of POVM. So I have the first measurement M1, second measurement M2, and the third measurement M3. And I quantify the incompatibility of these 3 measurements, and I subtract the incompatibility of only 2 measurements that I had before. That's the difference the gain that I can win by adding another measurement. And here I use a strange symbol because so this symbol means that I concatenate an ordered list of two POVMs with a third POVM. So now I have to specify the order of the measurements. I do the first measurement and the second measurement, and later I add the third one. And that's just the concatenation of these POVMs. And I'm just showing you one result without explaining the proof properly, so we could find an upper bound on this incompatibility gain. So an upper bound is the incompatibility of a certain other measurement that are called n here. And this is a concatenation of three measurements for the three possible subsets, 1, 2, 1, 3, and 2, 3. And again, I have a new notation. This hash, the upper index hash, means that it's the closest jointly measurable assemblage to a previously given measurement. So now I have a new measurement that is the concatenation of jointly measurable sets of two measurements, but this whole thing does not need to be jointly measurable. So maybe I should show you a picture to explain this better. And this is a picture that, again, I took from another paper, and it probably reminds you very much of the entanglement picture. So what do we see here? We have three sets. So the jointly measurable set of measurements 1 and 2, the jointly measurable set of measurements 2 and 3, and the jointly measurable set of measurements 1 and 3. In the intersections, let's say here, we have two pairs jointly measurable. In the middle intersection that I'm following now with the laser pointer, you have that all three possible pairs are jointly measurable. And inside in this red circle, you have the situation that not only the pairs are jointly measurable, but the three measurements are jointly measurable. This is not the same. So this circle is not identical to this intersection. Good. Then you can take the convex hull, this dashed line between these three pairwise jointly measurable sets, and you would still call them, well, I don't know what you would call them, but anyway, what is outside of this convex hull of these pairwise jointly measurable sets, they are called genuinely tripartite incompatible. Good, this is not new, this picture, but just to illustrate. And what we could do now is, using our distance measure and using the triangle inequality, is to derive this upper bound by two tricks. So we split the measurement 1, 2, 3 in three pairs of measurements. And then we use the triangle inequality by introducing this point here, which is called n, and then saying that the distance to this point plus the distance to the jointly measurable set upper bounds this dashed line, and this dashed line upper bounds the real incompatibility of this original set. So this is too fast to understand, just to give you an idea of what one needs, what are the ingredients to prove this. So we have an upper bound, and again, let's show a nice picture to illustrate that. So here what you see is basically the situation that I explained before. You start with two measurements, let's say BB84. You make projective Pauli measurements, let's say in X and Z, doesn't matter which ones, let's say in X and Y direction first. So you make two measurements, and then you get the incompatibility on the vertical axis versus the noise parameter eta on the horizontal axis. So I mix these perfect measurements with white noise. And eta, if eta is 1, I have no noise, and if eta is 0.5, I have noise equal to 1/2. So here on the right side, noise parameter eta equal to 1, you have perfect measurements, and the incompatibility when you have two measurements, let's say X and Y, is given by a certain value, and then if you increase the noise, you go to the left, and your incompatibility decreases until a certain point when it becomes 0. And at this point, the operators do not commute. This is my example that I promised you before. The operators do not commute. Nevertheless, the incompatibility is 0. Okay, and the the purple line, the violet line, is now the case where you have 3 measurements, so you add the third measurement in that direction. Again, you can calculate the incompatibility, which is higher than before. It's the purple line. And in this case, the inequality that I showed you before is tight. So the difference between the purple curve and the blue curve, it's this red curve, and this is exactly this delta I, the gain in incompatibility that you win when you add another measurement. And this is going to be hopefully soon on arXiv. So we are doing the last steps to finish the manuscript. So we have an upper bound on this incompatibility gain, and we also have some lower bounds. So let me just show you a lower bound. And I'm sorry, but here's a typo. So the result for the lower bound is that the incompatibility of this measurement assemblage for 3 measurements, it's larger or equal to 1/3, and now here should be incompatibility, the diamond incompatibility of M12 plus incompatibility of M13 plus incompatibility of M23. And how do you prove it? Again, you use properties of the diamond distance, you use convexity. Let me not go into detail. So how do we interpret this? Coming back to entanglement, I think all of you know these famous monogamy inequalities. If you have a tripartite entangled state of Alice, Bob, and Charlie, if Alice and Bob are highly entangled, then Bob and Charlie cannot be highly entangled. So somehow the entanglement in one subset bounds from above the entanglement in the other subset. And here it's different in the following sense. So we called it a kind of polygamous nature of incompatibility. If you want this assemblage of 3 measurements be highly incompatible, then all of the subsets have to be incompatible, because otherwise, also on the previous slide when you had this upper bounds, again we had these 3 possible subsets that bound the incompatibility of the whole. Intuitively, this is again clear. If you want to make your measurements as distant or as bright as possible, each of the subsets has to be incompatible. But this is now quantified by certain inequalities. And here I just showed you some examples for 3 measurements versus 2 with equal weights, but you can generalize everything. So you can have inequalities for more than 3 measurements. You can use weighted measurement assemblages, but I didn't want to show all these technical details. There are some proofs that soon you will be able to read up. And I think this is now really all I wanted to say. And let me summarize and give an outlook. So I think at the moment there is quite a lot of work going on about resource theories of quantum measurements. And we suggested a quantifier, the diamond distance, to somehow make a unified framework of all these different resources of quantum measurements. We found the hierarchy for these measurement resources. Informativeness is larger equal to coherence, larger equal incompatibility, larger equal steerability, larger equal non-locality. And within SDP, we've found numerical solutions, certain analytical bound solutions, in particular for MUB measurement assemblages. And there are several future interesting directions. What is the relation to other resource theories, which I did not mention now, like imaginarity, for instance? Can we compare to other quantifiers, like there's not only robustness and distance-based measures, but also entropic quantifiers? And for the moment, I have no idea how to do that and whether it's possible or not, but maybe you have some ideas. Tightness of parts of the hierarchy I mentioned. Incompatibility gain, there are some open questions. So I think there is still lots of things to do, and I'm also happy to discuss if you are. I will be around also a few more days. And just come to my office if you want to discuss. I would be happy to discuss. Last but not least, this is a pre-pandemic picture of my group. We should really take a new picture because half of the people are gone and have been replaced. The size is more or less the same, but the people are different. But let me show you the most important figure in this whole work. This is Lukas Tendig. next to Heinrich Heine, by the way. This is Heinrich Heine, the famous poet after whom our university is named. Now they are proud of him, and when he lived in Düsseldorf, they were not proud of him. So it took some student revolution in the 70s. The students were protesting and they wanted this name to be adopted. The old professors didn't want to do it, but now it's established, and also the old professors are proud of Heinrich Heine. We have a competition every year, so we can vote for the citation of Heinrich Heine, which we like most. So he's there, and there is a statue next to Lukas Tendig. And there is also Hermann Kampermann, who is now running the group while I'm here. And I'm very happy that I have very talented, motivated people to work with to keep me as young as possible. Thank you for your attention.